So let's review those mixing times ideas. And so the long-time behavior of your Markov chain is related to ergodic theory, and ergodic theory is just about, in physics we call it statistical physics, statistical mechanics, and all those things. But ergodic theory is just a beautiful branch of mathematics, and you can use spin models. You can use it in physics very much. So the definition: the total variational distance between probability distribution mu and v and nu on X is defined as mu minus nu, total variation, is the maximum of mu of A minus nu of A. A is an event. So there is a proposition that says that if mu and v be two probability distributions, then mu minus nu, total variation distance, is just half mu of x minus nu of x. So it's just like L1 norm if you go to be continuous or even discrete. There is another important proposition that says that let mu and nu be two probability distribution on X. Then mu minus nu, the total variation distance, is half supremum of f of x mu of x minus f of x nu of x, where maximum of f of x is less than 1 for any x in your vertices. So I think I should talk about a very important theorem which is called Convergent Theorem in the book of Yuval Perez. A really beautiful book because it covers all the important techniques that you can find in order to understand and calculate the mixing time. And the lower bound, upper bound, also many different techniques that I will talk about it. But there are even more techniques than these one, and you can create your own technique as well. So a theorem about convergence, we call it Convergent Theorem because it's very important. So suppose P is irreducible and aperiodic. So this theorem is proved in the book of Yuval Perez. He has two books. The first book that is about mixing times and Markov chains. So if suppose P is irreducible and aperiodic with stationary distribution pi, then there exists an alpha between 0 and 1 and C greater than 0 such that the maximum of PT x and 0 for any x in your state space, the total variation between pi, which is your total, this is your stationary distribution, and ptx is just the transition after t step. So the total variation is less than c alpha to the t. So remember that alpha is between 0 and 1. So when t goes to infinity, this gets closer and closer to your stationary distribution. For example, stationary distribution is just a degree of x over 2 times number of edges, and it's a vector because it's just x is just one of your vertices. It has n vertices. So another important thing to know is the definition of d of t. D of t is the maximum of pt x minus pi, total variation. And these two definitions are very important. D bar t is the maximum of pt x minus pt y, the total variation. And there is a very important lemma that shows how these two, d and d bar are related to each other. You see, this is starting from x, the random walk starting from x. This is the random walk starting from y. But the lemma says that d of t is upper bounded by d bar of t. And d bar of t is upper bounded by 2 times d of t. Of course, everybody knows that d of t, something is less than 2 times that. But this part is important. Also, this part is also important because it says that your d of t is upper bounded by something that you call it coupling, and you use that coupling techniques to find that mixing time, and to bound it, and to control it. So the proof of this is very simple. You just need to use that triangular inequality, and you know that P of A is just P of Y for any Y, PT Y and A for any set A. And then just use the definition of PT X and A minus P of A. This is equal to, you can write this like saying that P of Y times PT of X and A minus PT Y and A. And this is upper bounded by P of Y, Y in X, PT X and 0, PT X, Y and anything. 0, I mean anything. The total variation, which is upper bounded by, and this is d bar of t, less than d bar of t. Now just take the maximum and you have proved that. So the mixing time is by definition T mix of 1 over 4. So T mix of 1/4 is T mix. But what is this? By definition, it is the minimum of T the smallest t, that the distance between those t-step transition probability and stationary distribution are closer than epsilon. So when they are epsilon close, the least amount of time that you should spend in order to make sure that they are epsilon close to each other is t-mix. For example, we have a graph like this. Because of these blocking edges, like this one, it increases T of mixing time. It increases. But look at another beautiful graph. This graph, it's just this, or just a click. So the mixing time is very small because you can go to any other state at least one or twice. But this one, first you should get rid of this bottleneck and then get rid of another bottleneck to reach this state x. For example, we go from y to x, then you should overcome these two bottlenecks. So it increases the mixing time. So mixing times is upper bounded by some parameters. For example, here you should see, distance is playing an important role. Wow, I conjecture that maybe the diameter is important. So we will go through these things step by step and see what parameters are important. Of course, if we are talking about all instances, so not just planar graph, not just a special type of graphs, for example, bounded tree width. We are just talking about general graphs. That's why it is interesting. So we are not restricted to some particular graph, some Ramanujan graphs, some planar graphs. We're talking about general graphs and mixing of that. Of course, because there are many different random walks that you can construct, so our theorems could be very different, because for example, a lazy random walk, for a simple random walk, for an evolving set that Yoel Perez has invented it very beautifully. All of these things have different mixing time. And coupling is just one of the techniques, one of the 10, maybe 100 different techniques that you can use to bound the mixing time. And a coupling of two probability distributions, mu and nu, is a pair of random variables x and y. And it is defined such that mu is just probability that x is just a marginal distribution. Nu is marginal distribution of y is equal to y. And coupling is useful because it's a comparison between distributions. And the comparison between the distributions is reduced to a comparison between random variables. So from a very complex stuff, such as distributions, you just reduce the complexity to just some tiny random variables. So mu minus nu, and you will see how this total variation could be related to that coupling, is the infimum of the probability that x is not y, such that x and y is a coupling of mu and nu. So it's an effective approach to obtain an upper bound on the total distribution. So let's talk about the lower bounds on mixing time. So the idea is that if possible locations of a chain after three steps do not form a significant fraction of the state space, then that distribution of the chain at time t can be close to uniform. So we want to find the mixing time, and let's define the maximum degree, maximum d out of x. So this is the degree, just the number of the set of y, px and y is greater than 0. And because the stationary distribution is uniform, we can observe that xt of x is bounded by this. And so we want to calculate the total variation as usual. Total variation. So it is lower bounded by ptx and xtx. This is the set of states accessible from x in exactly t steps. So this one minus p of xtx. So it is greater than 1 minus delta tx. And this is greater than epsilon. So take the maximum and you will see that T of mixing, epsilon mixing, is greater than log of x 1 minus epsilon log of delta. And for the irregular graphs, it is just simplified to log of d minus 1 because you have the irregular graphs. So this is just the upper bound. Sorry, this is just the lower bound. Lower bound for the mixing time. So now we want to talk about upper bound of mixing time. And it's just a lemma that says pt of x minus pi, the total variation is less than sx of t. By the way, sx of t is by definition, it is also called separation distance. It is just the maximum of 1 minus pt x and y divided by p of y. Oh, this reminds me, this fraction, pt x and y divided by p of y, when I think about it, it reminds me the construction of that Lovász-Simonovitch curve that used some order on this, and you created that curve, and he bounded that mixing, which was related to conductance. So bounded by phi to the t and some coefficients. But let's prove this lemma. It's very simple. You just rewrite in this form. Y in x, so p of y, you can rewrite it like this, pt of x and y, and then you just subtract, you can write it as p of y 1 minus